FalkorDB, the ultra-fast graph database, explained. Part 1. Before we talk about FalkorDB itself, let's understand the problem it solves. Why would anyone want a graph database in the first place? Think about the data you work with every day. People know other people. Customers buy products. Transactions flow between accounts. Real-world data is fundamentally about relationships. In a relational database, those connections live in join tables, and every hop you traverse means another expensive join. Ask a deep question, like friends of friends of friends, and the query explodes. A graph database flips this around. It stores the connections directly, so following a relationship is cheap, no matter how deep you go. FalkorDB uses the property graph model. Here's how it works. Nodes represent entities. Each node can have labels, like user or post, and properties like a name or an email address. Relationships are the edges between nodes. They are directed. They have a type, like friends, widity, and they can carry properties of their own, like the date a friendship started. There's no rigid schema. You can add new labels and edge types whenever you need them. And you query all of it with openCypher, the most widely used graph query language. So where are graph databases making a difference right now? First, generative AI. Knowledge graphs ground large language models and structured facts, making retrieval augmented generation more accurate. Second, agent memory. AI agents need to remember entities and how they relate, and a graph is the natural shape for that. Third, fraud detection. Because fraud shows up as rings and chains of transactions that are trivial to spot in a graph. And of course, the classics, recommendations and social networks. FalkorDB was built with exactly these workloads in mind. Part 2. Now for the beautiful idea at the heart of FalkorDB. A graph is secretly a matrix, and querying a graph is secretly linear algebra. Here's the key insight. Take any graph and number its nodes, 0 through n-1. Now build a grid with one row and one column per node. Put a 1 in row I, column j, exactly when there's an edge from node I to node j. That grid is called the adjacency matrix. In FalkorDB, every relationship type gets its own adjacency matrix, one for friendships, one for created posts, and so on. And once your graph is a matrix, something magical happens. Graph operations become matrix operations. Let's see the math in action. Take a vector v with a 1 for every node you're currently standing on, your frontier. Multiplying it by the adjacency matrix, v prime equals a transpose v, moves you along every edge at once. That's one single hop computed for all starting nodes simultaneously in one operation. Want to go further? Square the matrix. A squared tells you exactly which nodes are reachable in 2 steps, and even how many paths lead there. Friends of friends is literally one matrix multiplication. This is how FalkorDB thinks about every traversal you write. There's a catch, though. 1 million users would mean a matrix with 1 trillion cells. The saving grace is that real graphs are mostly empty. Each user knows a few hundred people, not 1 million. So almost every cell is 0. Sparse matrix formats store only the non-zero entries, which means memory grows with the number of edges, not with m squared. FalkorDB builds on GraphBLAS, a battle-tested library for sparse linear algebra, and it's the first property graph database to represent its entire graph this way. Let's follow one query through the engine. First, your Cypher query arrives as plain text. Second, it's parsed into a syntax tree and validated. Third, the planner turns it into an execution plan, a tree of operations like scans, traversals, and filters. Fourth, and this is the FalkorDB twist, each graph pattern is compiled into an algebraic expression, a chain of matrix multiplications. Fifth, GraphBLAS multiplies those sparse matrices together using every optimization in the book. And finally, results stream back to your client. From text to algebra to answers. If graphs are compact sparse matrices, there's an obvious problem. Inserting a single edge into a tightly packed structure can be expensive. FalkorDB solves this elegantly with delta matrices. Each logical matrix is actually three: the big main matrix, a small delta plus holding freshly added edges, and a delta minus holding recent deletions. Writes only touch the tiny deltas, so they're fast. Readers see the combination of all three. And a background process folds the deltas into the main matrix when it pays off. You get matrix speed without write stalls. A quick look at the architecture. FalkorDB ships as a Redis-module written in C. It loads into a standard Redis server and inherits everything Redis is loved for: speed, simplicity, persistence, and replication. Each graph lives under a single Redis key, which is what makes FalkorDB naturally multi-tenant. One instance can comfortably host thousands of isolated graphs. Queries are dispatched to a thread pool, so reads run concurrently, and indexing, including full text and vector search, is built right in. Part 3. Enough theory, let's get our hands dirty. Everything in this part follows the official Getting Started guide at docs.falkor.com. Getting FalkorDB running takes exactly one Docker command. It starts the graph engine on port 6379 and a built-in visual browser on port 3000, so you can explore your graphs from day one. The image bundles Redis 8, which FalkorDB requires. And if you want authentication, just pass a Redis password through the Redis RGS environment variable. That's the whole installation story. Next, connect from your favorite language. In Python, you pip install falkorb, import the client, connect to localhost on port 6379, and select a graph by name. If the graph doesn't exist yet, it's created the moment you write to it. Official clients also exist for JavaScript, Rust, and Java, and they all follow the same simple pattern. Connect, select a graph, and start querying. The Getting Started guide builds a tiny social network, and we'll follow along. It has 3 users, Alice, Bob, and Charlie, each with an ID, a name, and an email. It has 2 posts, each with content and a date. Users are connected by friends weighted relationships that remember since when they've been friends. And each post is connected to its author through a created relationship with a timestamp. Small, but it exercises everything: labels, properties, and typed. Directed relationships. Here's the whole network in one Cypher query. Each create line with parentheses makes a node, a label after the colon, properties inside the curly braces. So Alice is a user with an ID and a name. The last 4 lines create the relationships. Read them like ASCII art. Alice, arrow, friends weighty, arrow, Bob. The square brackets hold the relationship type and its properties, like since. Run this once through graph.query, and your social network exists. Now let's ask a question. Match is Cypher's pattern-finding keyword. You draw the shape you're looking for, and the engine finds every occurrence. Here the pattern reads: a user named Alice, connected through an outgoing friends voice weighty relationship to some node we call friend. Reader then projects out just the friend's name. In our little graph, that's Bob. Notice what you didn't write. No joins, no foreign keys, just the shape of the relationship you care about. Same idea, different relationship. This time we match Bob, follow his outgoing created edges, and land on nodes labeled post. We return the post's content property, rename to post content, and the answer comes back. Graph databases are awesome. Once you've internalized this one pattern, node, arrow, node, you can read and write most Cypher queries you'll ever need. Here's your Cypher cheat sheet. Nodes are wrapped in parentheses. Think of them as little circles, with an optional label after a colon and properties in curly braces. Relationships are arrows with square brackets holding the type. Match finds every occurrence of a pattern. Where filters the matches, and return chooses what comes back. For writing, cre adds new data. Merge adds it only if it isn't already there. Seti updates properties, and delete removes things. That's 90% of the language on one slide. Part 4. FalkorDB goes well beyond match and return. Let's look at indexes, vector search, algorithms, and the ecosystem around the engine. As graphs grow, you need indexes. FalkorDB gives you 3 kinds. Range indexes accelerate exact lookups and inequalities. Find the user with this email, or products under $50. Full text indexes, powered by Redis-search, tokenized text, so you can search it like a search engine. And vector indexes, the newest and most exciting kind, let you search by meaning, using embeddings. On top of that, unique and mandatory constraints keep your data honest at right time. Here's how semantic search flows through FalkorDB. You start with a plain English question. Say, a merciful judge waiting a pound of flesh. An embedding model turns that sentence into a vector, a list of numbers capturing its meaning. FalkorDB's vector index compares it against every stored vector, and the nearest chunks come back in milliseconds, ranked by similarity. But here's the graph superpower. Each result is a node, so you can immediately walk the graph around it, to its book, its author, its neighboring passages. Vectors find meaning, the graph provides context. And here's the entire vector story in 3 snippets. 1. Store an embedding on any node with the vec_f32 function. It's just another property. 2. Create a vector index over that property, declaring the dimension and the similarity function, cosine in our case. 3. Call db.edx.vector.query nodes with your query vector, and it yields the key nearest nodes with their scores. One subtlety. The score is a distance, so lower means more similar. 3 snippets, and you have a production vector store inside your graph. We put this to the test with a real demo built for this video. We took 3 classic novels, Wuthering Heights, The Merchant of Venice, and A Tale of Two Cities, split them into nearly 2,000 chunks, and embedded each one with Gemini. Every chunk became a graph node, connected to its book and to the next chunk in reading order, with its embedding indexed by FalkorDB. The result, shown here, is a searchable atlas of meaning. Ask about a merciful judge and a pound of flesh, and every top hit lands in Portia's courtroom, ranked by similarity, with 0 keywords in common. FalkorDB also ships classic graph algorithms as built-in procedures, callable straight from Cypher. Pathfinding gives you breadth-first search and shortest paths, the backbone of routing and dependency questions. Centrality algorithms like PageRank and Betweenness tell you which nodes matter most in the network, and community detection finds the natural clusters hiding in your data. Because they run inside the engine, on those same sparse matrices, they're fast, and there's no data shipping to an external analytics system. Let's contrast the 2 ways engines traverse graphs. Traditional graph databases chase pointers. To move from a node, they follow one edge at a time, hopping around memory in a cache-hostile pattern, and the cost adds up edge by visited edge. FalkorDB instead expresses the same traversal as linear algebra. A single sparse multiplication moves the entire frontier at once. The kernels stream through memory the way hardware likes. GraphBLAS brings decades of optimization for free, and the work is naturally batched and parallel. Same question, fundamentally different machinery. Around the engine sits a growing ecosystem. Official clients cover Python, JavaScript, Rust, and Java, all sharing the same connect, select graph, query pattern you've already seen. The built-in browser on port 3000 lets you explore and visualize graphs without writing a line of code. For AI builders, there are first-class integrations with LangChain, LaMDA, and the GraphRAG SDK. And you can run FalkorDB anywhere, plain Docker, Kubernetes, or the managed FalkorDB cloud if you'd rather not operate it yourself. Let's wrap up with the big ideas. First, the theory. A graph is a sparse matrix, and traversing it is matrix multiplication. That's FalkorDB's superpower. Second, the practice. With openCypher and a single Docker command, you're productive in minutes. Third, the architecture, vectors, full text search, and graph structure lab together in one engine, no gluing systems together. And finally, the timing. This is a database built for the AI era, for retrieval augmented generation, knowledge graphs, and agent memory. Thanks for watching and happy graphing.
If you like this video, please subscribe and share. Thank you.